let's talk about trees. Trees are a data structure that is very commonly used in programming. They're very similar to linked lists. Here is a basic layout of a tree structure. Every tree has a root node, just like a linked list. However, instead of just a single next pointer to the next node, a tree can have multiple pointers to different child nodes. In this case, we have a left pointer to the left node drawn here, and a right pointer to the right node drawn here. Each of these nodes can have their own children nodes, as shown here. Like a linked list, tree structures end when the nodes at the bottom of the tree have null pointers instead of pointers to the next children nodes. Next, let's talk about 3 common strategies for traversing trees. They are as follows: in-order, pre-order, and post-order traversal. Note that many implementations of these strategies involve recursion. Next, we will go over each of these strategies one by one. First, in-order traversal. The algorithm is shown here on the slide. First, we must process the nodes in the left subtree of the current node. Second, we process the current node. And third, we process the nodes in the right subtree. For example, if we had this tree here on the slide, we would process element B first, A second, and C third. Second, we have pre-order traversal. The algorithm is as follows. First, process the current node. Second, process the nodes in the left subtree of the current node. And third, process the nodes in the right subtree of the current node. So in our same tree example here, we would first process A, then B, and then finally C. Finally, we have post-order traversal. Again, here's the algorithm. First, we will process the nodes in the left subtree. Second, process the nodes in the right subtree. And third, process the current node. So in our example here, we would first process B, then C, and then finally A. The final topic that we will cover today is binary search trees. Binary search trees are a type of binary tree with specific properties that make them very efficient to search for a value in the tree. All binary search trees have the following property. For every node x in the tree, all nodes in x's left subtree must be less than or equal to x, and all nodes in x's right subtree must be greater than or equal to x. So take, for example, the tree we have below. This tree is a valid binary search tree. Why? Because if we take the root node 2, all nodes in 2's left subtree, which is just 1 in this case, are less than or equal to 2, and all nodes in 2's right subtree, which is just 3 in this case, are greater than or equal to 2. Of course, this is just a very small example of a binary search tree. If this were to be expanded, any children nodes from 1 would have to be less than or equal to 2, and any children nodes from 3 would have to be greater than or equal to 2. Lastly, before I conclude this video, I'd like to take you through a quick example of a problem involving trees. This problem is number 222 in LeetCode, and the task is to count the nodes in a complete binary tree. The problem is shown here. Here is a potential solution to the problem. First, we initialize a counter variable and set it equal to 0. This variable will count the number of nodes in this tree. Second, we initialize a tree node pointer variable, current, and set it equal to the root pointer that is passed into this function. Now, since this is a recursive function, we must have a base case. The base case is as follows. If the current node is equal to null, then we return 0. This is because when we traverse to the bottom of the tree, there will be no more nodes to count, and thus the function must return 0. Next, we have the recursive step of our function. We have counter plus equal, count nodes, current, arrow left. This is a recursive call. We add to counter the number of nodes in the left subtree of the current node. Next, we have counter plus equal 1. This is the code that processes the current node. Next, we have counter plus equal count nodes, current arrow right. This is the code that processes the right subtree of the current node. Now, of course, each of these recursive calls will repeat these steps. Finally, we return counter variable, which, at the conclusion of all of the recursive calls, and when all of the recursive calls return, should contain the total number of nodes in the tree. This is an example of an in-order traversal of our tree.